Okay, so this is the next one that we built. So this is the big brother of the smaller one that we showed. That one never we could operate above 1,000 degrees, very unstable temperature wise. So this one is a 1700 degree furnace. So we could easily stabilize it at 1600. This is how it looks. So it was done by Joanne Tanner, who managed the project. Once we finalized what we will buy, and she used it extensively for her thesis. Then the others followed. So what it is in here is this. It's a 9-zone furnace, so we can maintain any either an isothermal condition in there, or if we wanted, we can vary the temperature along the unit. It's about 4 meters tall, and then it's a 9-zone because you see those 9 separate temperature controllers, 1 to 9. And everything is driven from a LabVIEW software mounted on this computer. So we don't have to do any mechanical intervention, including the feeding from the top. There we had a different feeder. The previous fluidized bed feeder for this one wasn't working well. So we bought a new one from a German company, Barbender, B-A-R-B-E-N-D-E-R. Very expensive, but it really stabilized our system. Atmospheric. I don't want to go into pressure. My life is, I need to keep my life simple. Getting old. Now, as I said before, pressure effects are easy to calculate. You can easy to calculate and easy to estimate by different means. So better use something that you can use. And then next to it is the micro GC, this white bit in here. And I don't know whether you can see. Behind it is all its calibration cylinders on the same trolley, so that it can go from one rig to the other if we wanted to. Then we have, you see, the 8 different mass flow controllers here on the panel. Those can create, those can be utilized to send any types of gases inside. What does that mean? In the gasification process, you will have a lot of pollutants. So if you want to investigate that in the presence of this much ammonia or that much hydrogen cyanide or that much sulfur gases, how this will behave, then we use this, send gases through these mass flow controllers from the cylinders. Or if we when we do the different concentration of CO2 and and the balanced nitrogen or the other gases going in, we just use these ones, the mass flow controller. So we get an extremely accurate flow rate of what we are sending. That is very, very important. So this is one. This is now the workhorse, I would say. And this is a single tube, single aluminum tube. Each costs about 17,000 US, each aluminum tube. So we need to be very, very careful as to how we heat it up and how we clean it. Once it is broken, it is broken. You cannot fix it at all. And we have broken few. So this is, how did it happen? No, not by bad luck. Not by bad luck. See, older people do not break anything. So that's why I said that if you think you have a meeting with your girlfriend or a dinner with your girlfriend or your wife, and you don't do that. Take your time and wear that bit. Don't rush. The only thing it breaks in the rings is the reactors. Rapid heating. Always 4 o'clock already. Let's push them. Stop button, go home, and the professor is not there. Who cares? And then the next they will come and say that you are not detecting any change in oxygen, zero oxygen while you are heating. Because when you are heating, you are constantly monitoring it for zero oxygen. It has to be absolutely leak tight before. So if oxygen level is not decreasing, it can happen for 2 reasons. One is that you have damaged your microgas chromatograph, or it is leaking, therefore it is sucking in 21% all the time. And in most cases it is the alumina can. No, yeah, that's quartz. Quartz can go to 1100. Quartz. But this one is, it was designed for 1700. We operate at 1600 maximum. And you cannot drill any hole. I mean, if you drill hole, then you have to decide what for. Then you have to instrumentation. How will you seal it? Very difficult. Very, very difficult. And then not only sealing it, you're maintaining the seal. High temperature resistant seals are. Only thing is you need to screw things in. But alumina tubes you cannot screw things in. Starting from the bottom and starting from the top. From the top. No optical. So, not all action. But the CFD models will tell you that within that small radius, not much. Particularly when you're hitting it from the all around this periphery. Gas species measurement we have done very few actually by inserting probes, retractable probes underneath. So we could measure it at 1 meter level, 2 meter level, and at the bottom. Very difficult. Water quenched. So those probes are very special. Those probes are made, you have the water cooling system that goes in. And then on the top of the probe, there is a collection area, just like small crucible as if. Inside that, there is a thermocouple close to the tip, so that senses what the temperature of it. You can get only approximate indication. It will not be absolutely perfect because there will be a lag. And you cannot keep the probe there for indefinite period of time, while at the same time water is going also in. Quite difficult to do. Manually, we don't have the facility to do it automatic. I mean, one location, one at a time, one at a time. Constructed. Constructed. Not much, only about 1.5, 1:1.5. Usually 1:5 is fine, quite sensible. But of course, it depends on what you can put. Because you have already seen how tall the overall structure is. And I had to keep provision in the top, on the top as well, for someone to stand and then operate there safely. And also at the bottom, so there is a limit. And of course, budget. This is an entrained flow reactor. Yes, it is no drop tube business. Drop tube, yeah. Previous one. It's still operational. Don't use it. So here, here, now we have decided that we will not make it flexible. We will not make it flexible. We'll feed it right from one location and one location only. So right from the top, only from one location. So center dotted line. So this is the feeder. So this is the feedstock injector, that means the coal injector. And this one, this is a straightforward tube. No, nothing fancied really. It's just a 253 MA tube. These coal particles are coming with some parched gases. I mean, if the parched gases go in here, some of the parched gases can enter into the feedstock box also, but we don't allow that to happen. We simply keep it isolated, in parched gases in here so that no amount of oxygen can go through it. Only way the gas goes in, reacting gas, are from the cylinders going to the preheaters and to the through a separate injector at the top, side by side to it. And this is the gas heater, heater. We can move it, but during a run we don't move it. In today's run we keep it at that position. In tomorrow's run we'll deeper. That's how we can vary that. Because that gives us the experience, that gives us information. What works, what doesn't work, what is useful, what is not useful. At the end of the day, everything is useful, right? But all very high purity, ultra high purity nitrogen, ultra high UHP, CO2 and nitrogen. CO2 and high purity nitrogen passed separately through the mass flow controllers. So you can adjust what ratios you will be using based on your calculations, and that's what it comes. So we don't take any risk. There's the main collector vessel here where predominantly the char falls down. But the question you're asking about how the gas goes in sampling to the tubes. Lot of dry ice, plain ice, and then eventually there is another set with what's that column called, which the perma filters, which you can buy. This perma filter that takes out all the moisture. The beginning. Plain ice. Plain ice. Rice. This one also we can quench. It's absolutely quenching. Doesn't matter. If you use CO2, then what will happen is you really need to get a feel for how much CO2 is leaking from the parch into this, because that will contribute to reaction. But if you are feeding nitrogen, that will not contribute to reaction even if it leaks. No, CO2 will contribute to the overall reaction if it leaks inside the reactor. Oh, here, yeah. It is creating a pressurized environment so that outside air cannot leak into it. Standard part.
So what is
good question?
Why is there a cooling section in the top?
If there is not a cooling section in the top, then when the boys or birds they go over there and change, they their hands will be on. So the occupational health and safety they will not sign off on this because everything that we do, there is when we design a rig and build it, we have to take a permission from the university authorities. So we have to submit our design calculations, we have to do the risk analysis, we have to do the safe working instructions. I have to sign it off first after checking, then it goes to the department's safety manager. She signs it off then after verifying, asking lots of questions, then it goes to the university level. Then it goes to the, beyond a certain temperature, it goes to the state level. This goes to the state level. So they will not allow if any of the parts are over 60 degrees centigrade outside temperature. That's it. It's not only that. Say we have developed the RA and SWI for Saurav as the operator. And 2 months later, if Abhishek becomes the operator, you have to do it again. Even though it is the same thing, and or if it is a new feedstock, it has to be done. The idea is that the new person just understands what is involved. Because otherwise, if anything happens, someone will lodge an incident report, it will be investigated, and the consequences can be severe. Each and every one. It's fast process, not unduly slow, but it's there for a reason. So we'll quit from the top only. No. Well, not really, because it can, but at least it will. You can ensure with thermocouple measurement that what the gasifying gas temperature is going into the reactor. And at the end of the day, when you have calibrated the whole reactor, well before the tests have begun, and from time to time you do it, that with the furnace operated correctly at the right setting, you are getting inside the reactor the temperature that you want, that's fine. Because at the end of the day, if anything happens to the operator, which is a student, then the person who is responsible is me. So after 5 o'clock, any work that has to be done, I have to authorize it, even if I am here. And I have to then authorize that this will be the body with phone number, mobile phone number, and that body will always be there within 50 meters of the actual operator. And that I will also eventually be available, whether internationally or otherwise. So it's that strict, but it is for a good reason. Things have happened before. It's simply exactly as what happened in the industry. So any other question on this? This is sold by Juniper, Agilent. So I don't know, they don't have Agilent. That's the brand name. So you're quite happy. Maybe it's special. I will check. That will be separate much. Why were you using it again? Moisture removal is a kinetic process from cold or from the gas. So the problem is, if you have a very tall conducting system, maybe you can only one dynamic system. But we never say the micro GC $1,000. So protecting that one and the columns to replace them, $3,000–4,000 each it takes. So to replace, save that, it's much better to investigate, to be conservative. Right. So we have used it for many things, for different types of coal with high ash. I mean, our high ash is 15%, which is nothing. Some high ash coal, Victoria, low ash coal, Victoria. We have also used for petroleum coke for an IITB student. He went into it, and for biomass as well. So these are some of the coals that we use, but it's not to worry about it. Huh? Why isn't it going? Oh, I just skipped one. Yeah. So again, we are looking to the gas quality and the carbon conversion under different pyrolysis and gasification conditions, the contribution of different types of chemical reactions, the particle size evolution, and morphology change. So let's go one by one. The first one is easy, same as this. Second one, what I'm saying is in here is that alumina tubes, you can inject steam, not a problem. So you can investigate steam carbon reactions, CO2 and board water reaction, both, and the mix of that as well. So that's what I mean over there. Then the particle size evolution, we have taken particle samples at different locations by having the sample probe inserted at different levels for a certain period of time, and then taking it out, cooling it down, putting it again at another level, taking it out, etc. So that's how we do it. So these are the sort of things that we can play with over them. After they are collected through the SEM. Morphology, only way you can do it through microscope, either optical microscope or scanning electron microscope. That's what I know. So this is a typical short run, for example, done at 20 volume percent of carbon dioxide, rest nitrogen, and 1200 degrees Celsius, and you can easily calculate, as you said, how much substoichiometric it is at 20% CO2 for the flow rate that we use vis-a-vis the carbon feed rate from the coal feed rate calculation. But this is typically, this is my steady state period. How do we define that it is steady state period? When we see that the gas compositions have all more or less stabilized while keeping a firm eye on oxygen level, which should be 5% all the time, right? No, 0%. So sometimes I just test you guys if they're listening or not. That's fun. Okay, so this is very important determinant, because if it is not 0, then you are doing a little bit of a combustion. I mean, if it is 0, means you have consumed all the oxygen. That's the beauty of it. So here we call the steady state from this point, because only after this point we see that the gas composition is steady, even though we measured the gas composition all the time, and then later on decide where from I will take my reportable data. That's what we do. Yeah, well, I mean, no volatile, even in the volatile matter, you won't, under pyrolysis, you won't get any oxygen, because oxygen will come out as CO2. This one is gasification. But whatever you do in this Entrained Flow reactor, pyrolysis or gasification experiments, you have to ensure that your condition is oxygen free. Otherwise, it's not going to be pyrolysis. Otherwise, it's not going to be gasification. Because we are not mimicking a commercial gasifier in the truest sense. In the commercial gasifier, where is the heat coming from? From partial combustion of the carbon by using oxygen. Net result is 0 oxygen. Here, heat is supplied electrically. Either case, 0 oxygen. So that way similar, but subtle difference. But scientifically, we're still getting the same data. That's why we during the heat up stage, we continuously monitor the gas composition through the microgrid GC, while the condenser system is also on, that the oxygen content is gradually decreasing from 21 to so. No, CO2 and N2 we are not feeding in at that time together. We're feeding only the N2. That's it. So when we see that it has become 0 oxygen, it is time to inject coal or char, whatever be the case, together with your other reacting gases. So this is a departure. Next one is a departure from my normal slides, because I normally don't put too many words in my slide. That's my style, because that fixes your attention to the slide and not towards my lips, which I want. But I just copied it from one of the papers. So what it does is, it allows you to calculate this way the solid phase based carbon conversion calculation and the gas phase carbon conversion calculation. And both have to be done. Because if you say that this is my reactor. I know how much carbon is going in and how much carbon I am collecting at the end, and that will be my carbon conversion. Fine, that's one. But there is no guarantee that you are collecting all the carbon at the end, unconverted carbon at the end. Some may stay inside the reactor. So what you do, you also do the gas phase based calculation, then try to see if they are matching. In reality, they will never match to 100%. But if they are matching within plus minus 5%, it's good enough. But at least it gives a cross check. No one will be able to question you. No reviewer will be able to question you. You must do it. It's a very simple thing to do, provided you have the gas chromatograph giving you the right. So these are, what is that? This is the papers are looked at the high Eshkol Loyang and the low Yalon coal, the two low Eshkols, the pyrolysis behavior, so 100% nitrogen, looking at different temperatures, 1000 to 1200 to 1400, and it gives us, how much the char yield is. I mean, how much the carbon conversion is during the pyrolysis process only, as a function of temperature. And at the same time, you are getting what gas composition is evolving during the pyrolysis process as a function of temperature. And that's the important thing to have to start with. So if you have very well, with putting some effort, you have managed your reactor well, then the experimental part and the data collection will be a lot easier. So you have to put in a lot of effort at the front end to have a risk-free, day. And there is the other thing is sometimes some of the reviewers, and that annoys me most, when we submit a paper, some reviewers stupidly ask, how many times have you reproduced these experiments? It doesn't make sense, because in a continuous feed experiment, what is reproducibility? Every data point is the reproducible data point. It's only in the batch experiments you need to do it several times. This is continuous feed. So if I have taken 35 gas sampling points, and that's as good as 35 repeats. So always keep that in mind, but you will be asked that question every now and then, quite frequently. How do you do that? Oh, at my age, I have the luxury of, counter-punching. I can, on record, I can tell you is the one particular journal we submitted on waste processing, and then absolutely shabby comments came from the one reviewer. The two others were reasonable. They gave minor, and the other one is shabby. And then on that basis, the editor rejected it. So I read it, and then I wrote to the editor, dear so and so, the first name. Are you the editor, or are you a post box? Is your responsibility to just send the message coming from the sender to the post box to me, or see it, what is there, and then screen it and then send it to me? This reviewer has done a mockery of reviewing system, because this work is extremely labor and cost intensive. And not only that, it also determines the future career of a PhD student. It doesn't matter to me. I've got enough papers, but it matters a lot. So if you are sending rubbish comments, literally that's the word I used, then you are unnecessarily jeopardizing the career of a young researcher. He immediately sent back to his credit So please send it back, and then we will send it for a third reviewer, because I'm supposed to do it. Eventually the paper got published. So that's what I do. But, huh? Same problem. Why? If I think you are wrong, you are wrong. You have to stand for your own right. No one will give you leg space, standing space. But it really worries me these days. The quality of reviewing has gone down so much. I usually don't take reviews. I do a fair bit of reviewing, fair bit. I mean, every Saturday morning from 5 o'clock through to about 10, in my bedroom is my reviewing time. And we have to do it for our profession, and Shantanu, I'm sure, is no exception. Because if you don't do it, then the others will suffer, and then our students' work will suffer. Others, so why they'll do it? And we're doing it for free. But the thing is, you don't do a shabby job. If you do it seriously. Yeah.
Has to do 3 times the number of participants. At least 3 times. So that's what we do. But the important thing is to ensure not to give the reviewers any easy nitpicking claims, which if there are simple mistakes to a team, then obviously it sends a signal that you are not serious. And if there are things, but there are also unscrupulous reviewers also, and also unscrupulous editors, and one is from India. When you see the
chief of a journal, an Indian, one of the CSIL lab, publishing 100 papers in a year, theoretically impossible. Huh? Everyone. How many students one can have? 100 papers. I have seen, the thing is, there lies the problem. If you have not made any intellectual contribution, you should not be a co-author. You can be acknowledged, but there is some unwritten policy in some of the institutions. You name every Tom, Dick, and Harry up the chain as the co-authors. What they get? What they get? So in all of our papers, my students are the first authors, as simple as that. And where I take the editorial responsibility, I become the corresponding author. That's how it is. In some cases, when I see a senior student, and for his or her career, I give him the coordinating corresponding authorship too. And when they publish after they have got their PhD, I tell them, you become the corresponding author. I will be there to defend, but your career is now much more important than mine. So a lot of my ex-PhD students or immediately past PhD students, they are now becoming corresponding, because that's how they will get recognition. But unfortunately, it doesn't happen. This particular editor of a very highly reputable journal, he is simply milking the whole community in many, many countries by putting his name. It's not good. I'll tell the name later on. But it's not good. It is. Anyway, so this sort of information you can generate. And this sort of information also you can generate. This shows AB, and this panels in here. What is it? That effect of temperature on gasification behavior at 20 volume%, and syngas composition. So the CO concentration in here, CO concentration over there for different coals, and then here is the carbon conversion. The main message that I would like you to take is actually from here. This is what I'm very interested, is around By the way, these are all done at 7 seconds. That's in the paper, but it's not, I haven't forgotten, I forgot to put that in here. That where, at what temperature I am going close to 100% carbon conversion. That's my bottom line. Because gas composition will not vary all that much with carbon conversion, whether the carbon conversion is 80% or 100% or 90%, you will still get the same composition because it's the carbon which is giving you the gas, right? Through the reaction with CO2 and steam, etc. But it's extracting out the last bit of carbon available. That's most important, and that's why this is what I look at. So how it changes, you see, it drastically changes between 1000 and 1200, 200 degrees, and then subsequently it slows down, but nevertheless it reaches quite high level. And then from there, then we can, do all sorts of calculation to have the same information reported on the basis of carbon dioxide to carbon ratio and those sort of things. And that really tells you where you can literally stop with respect to the CO2 concentration, similar to the argument that you gave. So once you do the experiments and have very well controlled, the information from very well controlled set of experiments, you can literally represent your data in any shape or form you want to make it clear to your intended audience. These temperatures are essentially the gas temperatures. No, we are keeping it isothermal all along. Yeah. In a commercial gasifier, of course, it will vary, but what it is mimicking, if you can recall, we showed Mitsubishi's gasifier yesterday. It's a 2-stage. One stage, it is here, and there's the char falls. It is that gasification stage only. So this part is only that gasification stage, nothing else. That's what's most important to us.
Is formed, carried out isothermally at either 1000 or 1200 or 1400. Whenever we get 100% of those 100% carbon conversion, we stop it. And then we, again, different ways of looking at it, the carbon monoxide concentration, because this is all CO2 gasification. I don't have any steam gasification data to show you here, but we can represent how much maximum carbon monoxide we can get, corresponding carbon conversions, etc. It is essentially the same thing, but you can see how the variation of different types of coal. High ash coal is here. This one is a quite reactive coal. This one as well is a quite reactive coal. This one we had only one data point. We did not go to 1300 or 1400. So of course we got reasonable conversion there, as you can see from here. At 1200 we got pretty close to 100% conversion, so there is no need to go from that particular one to high temperature. So these are sort of the results, sort of the ways that you can present the results, and then you can put that into different forms. So what Tao showed me was that
first generate, as I said, he generated the char, kept them away at the same temperature that he would do gasification later on, kept them away, did that for a few days at a stretch. I mean, every day was a new set of experiment, but the system was kept on all the time. because thermal cycling is not good for the health of the reactors. So, and then put the char back again in a separate run. So, that's what two-step coal gasification means. First do the char, then coal pyrolysis to develop the char, generate the char, then do the char gasification. So, that's a two-step gasification, and this one is direct coal, right? So, what he was comparing was, I think yesterday someone was telling me that the char is less reactive than char generated from TGA is less reactive than the char generated from Diffraction, this sort of things and all. So, yes, it is actually. I mean, the char is less reactive than in situ than when it is gasified in situ during pyrolysis. So, that's what clearly it will show, that you will get in the two-step compared to the two-step which is here, you will get slightly more carbon conversion. So, if you can do everything in one go. But this is a fantastic information to generate. It is not unuseful. It is still a very good engineering data that what you should be collecting, how you would be interpreting, and that sort of thing, even though in reality this is the one which will be most useful. And then we did it at different CO2 concentrations, but never went above 20%, never needed to go beyond 20%. And then you look at the morphologies of the different chars in different ways from different, the one thing that I always tell my students, and that take a few representative samples of char, mount them on different stops. This in the SCM, you can easily put 10, 15 stops together side by side. You can mechanically rotate them, and for the same sample, it's much better to take the morphology and the EDX measurements at higher and higher magnifications. It gives you so much information. And you can literally see how the carbon has been depleting and how the mineral contents have been increasing as you do so. When you do the SCM analysis on a char prepared from 1000, on a char prepared from samples collected from 1200, on a sample collected after higher temperatures. So, literally. Can't happen, because in the fluidized bed, what also happened, additional dimension is time, which is not the factor in entrained flow gasification. It's all at different time, which is not difficult to do really. That's fine. What will happen is keep a position of extraction from the bottom, somewhere in the middle, extraction and then the valve there, and that valve will get that line will be filled with some stuff from the beginning. Keep that in mind. Then every now and then, stop the cold feed. Temperature will change. Help someone to take the sample, discover the first few grams, take the last few milligrams, then start working again. By that time, nothing will happen to the fluid temperature. There is no hard and fast rule for this. And as much as we
these are all engineering solutions.
It's just like knowing your own car, how you behave and how it behaves and how it behaves. The important thing is to not to get too overcomplicated, not to over automate. Keep it simple, and that you know what the the drawbacks are. And as long as you report them transparently, no one can question. This is how I have collected, this is there's nothing wrong in it. So that's one thing. And then the other thing that we can also do is how the particle size changes. So say, for example, we have here this yellowish line at the top is the char. Now, when you do the diffraction sizing, not so much in SIF sizing. SIF sizing, you have to plot it to get this. You have D10, D50, D90, etc. So does everyone know what that means? Yeah. You know.
Yeah. No. What happens is, say for example, this one. This is a particle size distribution. This is say D10. This is D50. This is D90. Which means this is the amount of particles. 10% of the particles are of this size. Are of this size. 50% of the particles are of this size. This size. And 90% of the particles in that volume are of that size. Then you have the other ones, the 3 to sort of mean diameter, etc., which is extremely useful for radiation interest calculations. So volume mean diameter D43. These are defined slightly differently. I cannot recall the exact definition of this, but it's a fairly very good relationship.
Then D32 is the numerated
D or 3
probability to the power of the probability of function of diameter of the particle multiplied by D cube
yes
dt in the denominator, the same thing is
square. So that's called the sort of mean diameter.
So,
is it like a cumulative, like D50 means suppose 50% particles are
in that range, in that volume that you have measured. So it's very important that when you do the particle size measurements, you actually repeat those few times by taking samples from
Sample container. If this contains all the samples, take some sample from here, take some sample from there, take some sample from there. Then you get a reasonably accurate representative samples of what you have got. So that's what D10, D50 is. So here you will see those numbers here, D50 and etc. That's what I thought I will put it in there. In that case, why he has written D50 volume in diameter, I'm not sure. He should not perhaps had written it. But anyway, so what it says is that, see, this particle size here has gradually shifted in that direction with increase in temperature, which is expected, nothing fanciful really. But it's a wonderful way of showing it that, look, this is happening. Okay. And sometimes you will see this sort of slightly bimodal happening as well. Slightly. In gasification, it doesn't happen all that much, but in combustion, I can tell you from my experience, it happens a lot. Gasification is a much slower process, particularly char gasification. So the shrinkage of the particles is a lot more controlled. That's why the shrinkage core model has evolved. Applicable in gasification, not applicable in combustion. In combustion case, if I had plotted all this, I would have seen two separate models, monomodals side by side. I would call it only valid for this, but definitely for gasification. Okay. Component definitely, but very difficult. In slow fluid bed, maybe. PF fired, no, because the particles will immediately fracture as soon as they go. In fluidized bed, slowly, with large particle, 5 millimeter particle or so, even more than that in some cases, they are gradually shrinking in size. Charred.
Combustion for modeling, what should we use for carbon combustion rate? I gave you a couple of expressions, similar type of expressions are used. You use it for with different partial pressures of the different gases that are present, but also there are combustion rates available. I think in one of the slides I have given one expression that led to the figure where we showed that for combustion in X very few seconds we get 100% carbon burnout.
But surface level is not the surface level. Actually, the heating will also not be able to surface level.
The sinking compound will not follow combustion.
So which model for change the surface level?
What do you mean by surface evolution?
So like heating compound is that surface is the material is compressing radially. So surface radiation is decreasing and the surface is only the reactive surface. Outer surface is only the reactive.
No, don't know for combustion. I can find it out and I'll tell you if you can find it on some of the
I have simulated and I have just used kinetics and one by of kinetics. Reciprocal average of kinetics, kinetic rate and diffusion rate.
in combustion.
And has given result 20% accuracy of the
Compared to what?
experimental
What experimental?
gaseous composition of CO2.
Are we talking about gasification or combustion? Combustion.
Entrained flow.
Yeah. So
With the CO2 concentration was axial, it was given as O2 concentration was given axial.
right. So the axial compositions were matching,
With 20% accuracy.
20% difference, and what was not matching?
The CO2 was not matching, it was matching 20%, it was the largest error. O2 was matching.
So maybe I'm not
So you are producing more CO2.
So maybe you are using the kinetics which is not valid for the So that's why you need to use the actual kinetic data for that particular field. That would be the only explanation that I would.
In our case of gasification model, we use the same model. So CU and S2, that came to be 5% of the chemical difference. But in our case, the methane was the main component that showed this difference. In volatilization, methane is predominantly produced from pyrolysis. That's we need to work on pyrolysis model.
Whether you would like to use a long-term pyrolysis model, which is very, very complex, or just take the values from the pyrolysis reactions and then concentrate more on the char gasification reaction, which is the slowest part of the routine. That's something that
So the values are also taken from the EGS chemical. It shows the
or you mean the char gasification kinetics?
volatile.
Oh, right. There are some data available in the literature where people have reported volatile measurements, the volatile fields, under fluidized bed conditions. People have actually measured small fluidized bed in the world, this small fluidized bed. So those will be more appropriate than TGA-based volatile intake. Because here we are talking about large particles. All the TGA ones will be small particles, and long period of time. There's differences. So doing a bit more search on the fluidized bed-based catalysis volatile composition, and then that will be much closer to. Then again, you have to look for the appropriate type of fuel. So that if your fuel is lignite, actually you don't use income by trees, that will be temperature is the guiding factor here. Operating conditions, in your rig, real rig, if it is 0.5, 0.6, someone has generated the data as 0.2, as long as the temperature is the same.
After gasification, whatever is collected, that has been sized in the diffraction sizer. So what it is showing is the original
chart, then how the size distribution has changed after 1000 degrees, how the size has changed after 1200 degrees, after 1400 degrees. So you can literally see that at that temperature, at those temperatures, how the size has changed. And someone can actually model this data, put this in some kind of algebraic model to come up with an expression for size evolution. And then try to see whether there is a need for adjusting any of these reaction models that are available, or just have a algebraic model.
This one's purely by fitting, curve fitting. So the information is there. It will be good if someone can do it, because we have about 16, 17 different coals that we have gasified so far. Then let me finish this ones today before we can go. Otherwise, tomorrow will be a very, very long day. Then we have again here carbon conversion on solids basis. Here we are considering, we also did a fair bit of work on biomass in Entrained Flow gasifier. PB stands for pine bark. And so one student looked at pine bark and Loyang coal, how they behave, whether there is any similarity or dissimilarities where they are. So that's what it is. And in this one, this is Loyang at 1200. This is a coal. This is 1400. And the second point. And then this triangle is pine bark at 1000. And this circle is 1200 biomass. So at 40% carbon dioxide concentration at this temperature, 1200, we got now almost 98% carbon conversion for the biomass. If we had the, I think what happened is they did also try for 1300 or 1400, 1300 I think we asked them, but they could not collect anything. So everything got converted and even the ash vaporized. So we had nothing to report, nothing to analyze and nothing to report. So, and then in here, what is it? Again, here the particle size distribution for the raw sample and the charts of pine bark biomass and the Low-Young. So this sort of analysis also you can see, and you can make how the shrinkage, etc., changes from coal to lignite to biomass, if you want. Then you can look at their morphology as well. What happens to it at 1200, what happens to the char at 1400. As you can see, it is becoming more and more ashy. It is getting covered with more and more minerals, so it will be not be reaching anymore. And you can see, when you see this type of things, you can then quickly do the EDX, and EDX gives you the elemental composition here. Okay, so elemental compositions through these peaks, and easy to do. And then for biomass, it's slightly different. Biomass gets very, very fused. And the reason it gets very fused is it has got, biomass has got a lot of potassium in it. Let me, while in here, as your memory remains in here, I hope we have, oh no, we haven't shown the ash analysis. So, but compared to the coal, biomass has a lot of potassium, and potassium is a fluxing agent. It reduces, and I think next one graph will show. So you then collect the char or the ash, whatever you collect at the bottom, you can subject it to X-ray diffraction. And if your sample is good, then you can see all the sharp peaks. So those who have done X-ray diffraction or will do X-ray diffraction is what? It only detects the crystalline compounds. It will not detect it will not identify any amorphous compounds. If it was an amorphous compound, lot of amorphous compound, then at the front end, instead of this, it will be like a big blob like that. So these samples were quite crystalline. It was becoming quite crystalline with passage of time. And what are those compounds? These are that the diffractogram represents. These are the ones you can't read them, unfortunately. These are the ones that are detected, and then what you can do is, okay, this is fine. Then you can do is you can then search the literature, list all of those compounds that have been detected, and then look at their melting points. Okay, so one example is classic is this one. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So this one has lots of potassium and sodium in it. See, it melts at a very low temperature. So even if it is present at slightly low concentration, it will change the behavior of everything. It will become more sintered, simply because of that. Whereas if it is high level of alumina, this char sample, which has also been detected, and if there are a lot of them, it will not, because its temperature is quite high. So that's one of the points that I was making a few days ago. Remember, aluminosilicates, not a problem. These are the good boys. Is these two, and iron. So this is a very. I thought it will be very good to have that kind of information out in the middle. This is not our measurements. Obviously, these are all from the literature, and then it's all been cited later on. But these are all that are detected, and corresponding melting temperature we have taken from the literature. We have put it out there in the open, and then we are saying that yes, these are present, and therefore you may have problems, may not have problems of sintering. So have I been able to give the message clear? That's basically it. So the last bit of gasification that I want to talk about, as you can see, I am very enthusiastic about gasification. Actually, if I start on the viscosity now, it will take up to 2 hours. So that will require a fair bit of effort. Let's do it tomorrow morning.
It's the discussions which is interesting for me. So let's set the scene for tomorrow. So we are still staying with the Entrained Flow gasification. It's good to say that this is the temperature required for this core, this biomass, petroleum coke. I haven't even presented anything on petroleum coke. That this much residence time and this much temperature is required for achieving 100% carbon conversion, high carbon conversion. And accordingly, what is the gas composition? That's the only thing that I have discussed so far, right? Nothing else. That's one side of the story. In the Entrained Flow gasifier, what I said, you have to remove the ash as molten slag. So the slag has to be a freely flowing slag, but it should not be very freely flowing so that it does not protect the tubes, but it should not be very slowly flowing so that it overprotects the tubes and that increases heat transfer. So there has to be a limit or range, for the viscosity of the slags applicable for a 25. Yeah. So 25 Pascal per second is the target. It's actually 100 to 250 flowing. So 25 Pascal per second. That's all. So that will be my starting point for tomorrow's presentation. What I intend to do is, I first intend to show you some of the existing models developed from the time that I was born and still being developed, and how those can be applied or misapplied to certain things, and therefore what can be done for to avoid misusing those, and therefore if there is a need for measurement, then how we can do it. So that will be the focus of tomorrow morning's presentation. So it's the other side of the gasifier, where the unconverted char falls, ash falls, and you need to melt it so that it can flow it out. You can flow it out. You can flow it out. But also at the same time, this is the temperature that you need to form or maintain at the reaction zone. That temperature can be lower than this gasification temperature for carbon conversion, or even higher than that. So you need to know both sides of the story. Otherwise, you may get carbon conversion, but nothing will flow out. The gasifier will then will die of over storage. So that will be the basis for tomorrow's morning's presentation, or the first half. Second half, some of you guys will be presenting. So who are presenting now? Raise your hand. Who are presenting tomorrow? What is the pending class?
One day classes, that's why so we can manage.
So
1 or 2 hours.
Oh, only 1-to-1. One to no. he already covered.
I think I'm covering what I intend to do. I'm doing it the right pace. We have got the entire next week as well, which I
Even Friday, there are
specify.
last 2 classes which are basically planned. Depending on whatever topics are not covered.
So what we still be covering the oxy-fuel, chemical combustion, oxy-circulating fluidized bed,
Fuels and
direct carbon fuel cell, and also chemicals,
or just
and the fuel gas cleanup. So fuel gas cleanup, if they cannot do it tomorrow, then obviously will do first thing on Monday morning. But we'll be fine for Saturday, late afternoon finish. Sorry, Friday later, next week.
So who are going to present tomorrow? 1, 2, 3.
So those who are presenting tomorrow, they have the luxury of presenting as much as they like.
How about you guys?
My topic is not.
Doesn't matter.
Actually, I have not started any experiments or I have not.
So it is a good beginning probably.
So what have you started on so far? Literature.
Yes, literature.
Let's hear the literature. That's what we do after 6 months.
It's our PDTF man. No, he's not the PDTF man. Oh? Yes. Okay, so let's get started. Okay. So we stayed on we discussed everything that we needed about the Entrained Flow gasifier up until this point. So I thought I would, in this one, I'll share a bit more about why is this misbehaving because of this, I think. No, I have the pointer. I'm charging my mobile, that's why. So I thought I will share my experience.
To gasification, you tend to try not to supply any material.
Gasification is overall a endothermic reaction. So you would not like anyone else to get a hold of the exothermic heat generated by the precious carbon in the coal, right? So purely from that philosophical view and also technical view, you would like to have no bed materials. So fixed bed gasifier, no extraneous bed material, but the bed is there, which is composed of coal, char, volatiles, and the gas. Fluidized bed, slightly different, no bed material. I'm talking about gasification, no extraneous bed material, that means no sand, no alumina, etc. But here, the bed itself is moving quite fast compared to the fixed bed gasifier. There, the bed is composed of incoming coal, unconverted carbon or partially converted coal, the volatiles and the gases, and of course the fluidizing medium recirculating. And even if in the bubbling bed, you are supposed to send some gas for fluidizing, so that will be also part of the bed. In entrained flow, it is a very lean solid concentration, and there everything is moving very fast, so no bed as such. So that's why we say fixed bed, fluidized bed, but we do not say entrained bed. We say entrained flow. So that's why. So yes, that's right. So localized, there will be heat generation, but for a flame to form and to be sustained, you need to create a certain condition. That condition is never met in a fluidized bed environment. I do not know the exact reasons for it. Maybe I will try to find it out and then come back to you tomorrow. No flame. So no flame means you can actually look at through the openings if you can, but you will not see any flame. You will only see glowing solids. Entrained flow, fixed bed gasifier, fluidized bed gasifier, entrained flow gasifier, fluidized bed combustor also. There is not a flame as such. But in a PF-fired boiler, you will see the existence of a flame continuously. One is PF-fire. Entrained flow gasifier is substrate, roughly 0.3 of stoichiometric ratio in terms of the oxygen content.
Could it be due to flame going?
Let me find it out and give you a more definitive answer tomorrow. I may not be able to same, very similar size to PF-fire boiler. Stoichiometry is the main difference. Velocities are more or less the same, about 10 meters per second.
PF-fire
around that is, if you regulate, not everywhere, it's nearly the throat region, not everywhere.
and I think the difference between fixed and moving.
Nothing actually. I don't know why they call it fixed. Yes, that's right. Because it's not as if it is fixed. Fixed to us, it means it's not doubling, it is not going anywhere, it is simply sitting and combusting. But actually, it is moving down. But it is moving as a fixed slug. That's how it is. So in that sense, it is fixed, but that fixed slug is actually gradually moving and moving down.
You are saying substoichiometric with respect to the oxygen requirement of the combustion. Right? Whereas here we are doing only gasification.
Correct.
That is why already we are supposed to operate. Plus, I mean, that every time it circulates. But it is not the reason. I mean, being the cold returning to the bed is not the reason why we are.
No, cold returning to the bed is not the reason. The only reason you are doing substoichiometry is that you don't generate too much carbon dioxide. Because the purpose of gasification is to reduce carbon monoxide as much as possible, along with hydrogen and only combustible constituents, not CO2. CO2 is not combustible constituent. So if you go stoichiometry-wise, if you approach one, then obviously theoretically everything will be combustible. But if you go down and down and down, you will not be able to supply enough heat, because C plus O2 is the only reaction that is generating heat needed to sustain the other chemical reaction. You can literally say that PF-fire is an entrained flow furnace.
But
even in the PF case, you actually are entraining the particle together with the oxygen, the gas there. So the entrainment is there, definitely it's not there. It's not that the gases are moving ahead or the particles are moving ahead of the gases. And then the bubble bursts. Yeah. In fluidized bed gasifier, that can occur. That does occur. Correct. So in fluidized bed, whether it is combustor or gasifier, that's what happens. Entrained flow gasifier, no. Yes. Oh, your question is where are the bubbles coming from? Gases. Yeah. Yeah. Up to a point. Up to a point. And then all on a sudden, when the bubble, because of the pressure rise internally, bursts, then the bubble loses its character, and everything becomes fully fluidized as far as those particles are concerned inside that bubble. Yeah. So what's your question on elutriation? What is elutriation? Oh, elutriation. Elutriation is nothing but what goes out of the bed, elutriating, moving up, and then going ahead. So that's what elutriation is, nothing else. So elutriation, as I mentioned yesterday, I think, elutriation can be problematic because if there are far too many fines, and if they elutriate away from the reactor, then those fines are not getting the chance to get reacted. So you would like to avoid elutriation as much as possible. How you can do it? One way is to entrain the particles within the gas. And that's the beauty of entrained flow reactor. Then the gases are not allowing the particles to elutriate away. Because if they go away, they're going away with the carbon, which is a loss to the system. Right? And that entrainment is the function of the gas velocity and the particle size.
Essentially, the task boils down from that the pressure difference should never increase the volume. So that burst never happens.
Oh, in the entrained flow, there is no bubble. Your velocity itself is so high to start with that you are not allowing the bubble to form anyway. And why you don't allow it to happen? Because the particles are small. Fluidized beds, the particles are an order of magnitude larger. For example, in fluidized bed, you are looking at 5,000 micron. In entrained flow, you are looking at mean 50 micron. So about 1:100 reduction. Huh? 10 to 100 micron. 10 to 100 micron. So, entrained flow gasifier and pulverized fuel fired furnaces, to some extent they are similar as far as the particle size range is concerned, but the only difference is the stoichiometry. The major difference is the stoichiometry. In one case, you are not allowing the carbon dioxide to form any more than it is required to generate the heat. In another case, you are trying to generate as much carbon dioxide as possible to generate as much heat as is possible, so that you can extract it to generate steam and then use it in the Rankine cycle for power production, electricity production. What's your first name? Abhishek. Abhishek. Okay. I did not want to write it before, so that so can you read what I have written?
Did everyone hear? Aim high, work smart. Not have to work hard, but to work smart. The most important thing in life is because otherwise no meaning of our existence. Then you flourish, others will flourish, society will flourish, country will flourish. Okay, so any other question before we move? So this, those who came late haven't missed much. Here we are going to talk, share our experience of operating drop-tube furnace as well as Entrained Flow Reactor. And there are distinct designs differences. So these are all our own built and our own operation. With the exception of welding, our students assemble everything. So the purpose of this was we were asked by a Japanese multinational to look at the analysis and gasification behavior
and brown coals, which some of the qualities of those brown coals, I mean the composition, I have shown before, right? Some have very high iron content in the ash. Some have very calcium content high calcium content in the ash. Some have very high silica and alumina in the ash. But all of them, when they are dried, they have very little ash. Only 2% or 3%. But within that 2 to 3%, there is considerable variation in terms of the chemistry of the ash. In particular, the iron oxide, calcium oxide, and aluminosilicates. So the purpose of this was to look at the effect of the different coal types, because in gasification, which is a much slower process than combustion, and if you can recall from yesterday's slides that in gasification you are looking at 1,000 seconds for complete carbon conversion versus few seconds in combustion. So it's an order of magnitude slow process, the gasification is. So the type of coal makes a huge difference in gasification. So that's why we are asked to look at coal type, effect of the temperature, and what that is, effect of the atmosphere, and to what extent you can have the substoichiometric substoichiometric environment. On what? On those second level bullet points, the properties and reactivities of the solid products, which can be char and ash, the carbon conversion, the most important statistic, the gas composition and the gas yield. These two are different things. And of course, the most important thing is pollutant gas emission. Those were the objectives given to us, and we decided collectively with our sponsors, because with the pollutant gas emissions, you need to know that information in order to design the gas cleanup system. Whether you want to use the gas cleanup, the gas eventually for gas turbine for power generation or for chemical synthesis, you really need to know how much pollutant species are there to start with. And what are those pollutant species, if you can recall? The sulfides, hydrogen sulfide and carbonyl sulfide, not sulfur dioxide in gasification, hydrogen cyanide, HCN, ammonia in particular, NH3. So those are the major ones. So we need to know how much is generated in the first place before we can design the unit to tackle those to an acceptable limit. And then the most important thing is at what temperature and at what residence time can 100% carbon conversion be achieved? That's like another important determinant. So that's what the second bullet point is in here. Okay. So these are our broader objectives, but of course within those broader objectives, we will also find some of the unknown problems. That's what always happens in any experimental work, or for that matter, any research. You have some known unknowns. These are all known unknowns as far as our research is concerned, but you also have some unknown unknowns which you discover or identify along the way. Okay? So these are the broad objectives. We have published quite significantly, I think, on gasification alone in the last 4 years. We have 4 students who have completed their PhD and now work in industry and other places. And we have in excess of 10 publications. But the ones that I'm presenting here are mainly from the last couple of years. The work by Tao Xu and Pramod and also Dr. Joanne Tanner. Dr. Tao Xu and Pramod, Joanne Tanner, they have got their PhD already. Pramod has just submitted. So we have widely published and it's available. And if you go to my Google Scholar, then you can, from that link, you can easily download. Anyway, so this is all experimental work. We have another group who looks at the experimental data and then do the CFD modeling, essentially to validate this for the larger one, not this one, the one that is on the screen right now, but that clearly is done to validate the model with the intention or expectation that at some point of time that those CFD models can be utilized for scaling up purposes. But predominantly 90% of the work is modeling, experimental. A little bit of modeling work has gone on, but the work that I'm presenting here are all experimental. Any question before I move? So this is one of the early setups that I built when I came to academia. We made it a bit flexible. You can make it to work like an entrained flow reactor, but predominantly at all sorts of gas flows, it works only as a drop tube. And as you have heard this morning, Stokes' law, which you can calculate based on the properties of the particle, the gas densities, and the particle size of the size of the particle. You can determine whether under a certain condition the particles will drop or the particles will remain entrained, and then the particles and the gases will move together in the process, getting reacted, getting the maximum opportunity to get reacted. So that's the difference between drop tube and entrained flow. So in as much as drop tube has its place in understanding the mechanistic parts of the entire process, drop tube is not what will you expect to happen in a real commercial gasifier. So we moved away from it later on, but nevertheless this one gives us a lot more flexibility. So this is only about 2 meters tall, and I deliberately went to atmospheric pressure because handling materials at high pressure is a challenge. I have operated pressurized drop tube furnace before in my previous employment in the industry, CRC for lignite. We designed for 25 bar, but we could barely run it over 10 or 11 bar. Holding the pressure is an engineering challenge which the students spend their time for unproductive purposes. My personal view is that you can literally calculate, estimate very well the pressure effects by other means. Therefore, you'll be much better off to keep life simple and design, build, commission, and operate something which will work reliably, will give you data which is scientifically accurate and also engineering-wise useful. So, what is this one? Okay. So this is by two different means. One is by calculation. Then we also had high-speed video, right at the different levels, right at the bottom and right at the top. And you can literally synchronize those two to get the exact time what you are getting by you are injecting particles from the top. No, not one particle, because single particle is not possible in here, but we are feeding it about, say, 0.2 grams per minute. And even for 200 milligrams per minute, which is 0.2 grams, is quite a number of particles. But as long as the particles are within a very narrow size range, it is fine. So you can make an estimate for the So I'll come to that. So this one is very flexibly designed. So the inside that we have the quartz reactor. So this is the bit, and then we have come in here, and then we have correct. So we have the secondary gases denoted by the red arrows, and then they then go to the top. The purpose is to ensure that they are getting heated inside. And then they enter the top through the top of the reactor, quartz reactor. And quartz reactor is literally, you can see it's a transparent thing, very expensive. Once it breaks, you lose about $4,000. And then it goes, and from the top we have a feeding system which can be adjusted. The feeding height can be adjusted from run to run, not in the single run. So we can either put it lower one injector here, or in another run we can here, lower it here, or another run we can lower in here. This is a completely electrically heated furnace as denoted by this. And at different, at different levels, we have the visual ports here, 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 and here. And at each of those levels, we have the optical parameters. We use 3 color parameters. It's simply by measuring the intensities at 3 different wavelengths. You can do it at 2 color parameters as well. 3 different wavelengths. It gives you a slightly better indication about the temperature. Eventually, you have to calculate based on the intensity. So we have the provision to have the optical parameters going there, or the high-speed camera, but not both. So the first thing that we do is, once it is built, we first do the calibration runs for the temperature, that how much temperature it goes as a function of the gas flows, the secondary gases, the primary gases, etc. Primary gas is used to illustrate the particles from the. These are very new batteries, only 2 days old. Don't worry. So you have another one, right? Okay. Need to be charged a bit. I think they're not rechargeable anyway. But I need only the I need only the laser pointer rather than anything else. না ব্যাটারি না, এটা দিয়ে কাজ করো, ব্যাটারি দিয়ে তারপর ব্যাটারিটা আমার সাথে চলে যাবে। Okay, so yeah, so it's a very special cold feeder, because you are looking at the fine particles to be elucidated at a very well controlled rate. This is scientific experiments that we are doing, so everything has to be very, very well controlled. And if your feed rate is a guesstimate, then your results will be guesstimate. So the primary gas, this is called a fluidized bed feeder. The primary gas goes in there and fluidizes the particles. You calibrate it first separately to see how many particles per minute you are elucidating under cold conditions as a function of different gas flows. Then from there, you get a good idea of what should be your gas flow rate in the primary feeder versus the actual coal feed, or for that biomass feed, or petroleum coke feed. So every time we change a type of coal, we need to do that. We cannot decide that student A has done it and put it in the literature, in the paper, therefore student B or C or D will do it. No, you never do it. So you do it every time you change a coal, or even better, every time you start a new campaign. When we start a new campaign, we usually go for until it finishes, not one day here, 3 days later, another one there, etc. So anyway, so this is a very well instrumented rig with high-speed camera, actually being able to detect the ignition of the particles as they drop. They can detect, the parameter can detect what the temperature you are measuring, what the temperature you are actually seeing inside. And of course, this one can record the whole event from different points. So everything that goes in through that point can be recorded real time for as long as you want it to record. Similarly, everything that comes in here can also be recorded. So you can actually get a history for the particles. It's a set of particles journey from the entry point, more or less, to right to the end, simply by looking at the video recording, high-speed video recording at the top, high-speed video recording at the bottom. Okay. And then the other thing that we have, so this is a downflow co-current, gas and particles going down simultaneously from top to bottom. Then at the end, we have a small catcher, particle catcher here. Then we have a thimble filter here. You know what thimble filter is. These are made of cellulose, so they can capture the particles. And then at the other end of the thimble filter, we have the online gasifier, gas analyzer, and then the other gases can be vented out. So you only direct as much as is needed by the gas analyzer, micro gas chromatograph, for example, for its detection. The most important thing is for the micro gas analyzer, or for that matter, any gas chromatograph, is to calibrate it every morning of the campaign. Because once you have run it for 6, 7, 8 hours on a day, and that's what minimum it takes, then you have, to some extent, you have degraded the column through which chromatographic separation occurs. So the nature of the column has changed in day 2 compared to day 1. And you need to appreciate that, and therefore you need to recalibrate the next morning to develop the actual baseline on that particular morning. Otherwise, the results can be quite anomalous. So that's the bit of the description. Very easy. So how it is controlled. So this one goes only up to 1100 degrees centigrade. That's how we designed it. But we have never operated it above 1000 degrees simply because we could not calibrate it. We could not control it. So the question is, how did we measure the temperature of the secondary gas and control it? So controlling is very easy. Measuring is the difficult part. So what we haven't shown in here is that we have thermocouples here at the entry point, which always tells us what is the entry temperature, which is close to ambient temperature on that day at that time. By the time it comes out from the other end, you also have the thermocouple there. You can use also the laser guns now. We did not have those at this time. These days it's very, very cheap, about $400–500. You can measure the temperature, even though you need calibration. But thermocouples at the front end, thermocouple at the back end, those two measurements will give you what temperatures you are getting for the amount of gas that you are sending. And here we have several mass flow controllers. You see the mass flow controllers, so it should not be shown. So we have several mass flow controllers in the gas lines. So, and the mass flow controllers are very, very accurate to the extent that you can control them to 0.01 gram per minute. So we are, this is all isothermal, the entire thing. No, it is going. So this is the furnace. This is where the heating elements are. So So what's happening? Okay. So secondary air is going at ambient temperature from this point. As soon as it goes inside, it starts to heat up. Its temperatures can be monitored at every point if we want to. And that's what is part of the commissioning runs. That's what the part of the calibration runs. How do we do it? Because we have the parameters available. Because this is only a 75 mm diameter, the distribution is very uniform radially as well as axially. No, radially we cannot, simply because you cannot penetrate through the quartz reactor. Not in the middle. For a species concentration, we have a different measurement system by inserting probe from the bottom of the reactor. That's for the bigger rig. The larger rig, the larger one, which I'll show later. Yeah. So this is where all the particles will be collected here as well as in here. So this is as you can see, this is slightly like a very small cyclone. It separates a little bit out, that stays there, and then whatever gets carried over eventually is captured here. And that's very, very important to capture. First of all, that captured amount for further analysis will determine what the carbon conversion is. Secondly, your microgas chromatograph needs a squeaky clean gas. Otherwise, it will get clogged, and that will be the end of it. It's actually quite simple. No plunger. No plunger. So the way it works is it's a small bubbling fluidized bed. Okay. So in a bubbling fluidized bed, what's happening? Nothing is circulating. It's not very fast. Bubbling bed ranges about say 0.2 to maximum 1 meters per second. But you are not even there. You are just staying slightly over the minimum fluidization velocity, UMF, and you are simply fluidizing it at different rates and collecting at the other end in separate runs to see how much you have collected for a given period for a given constant velocity, which is measured by the mass flow controller. So you pre-calibrate it before the run. No, not center pipe. Centrally, the gas goes here over the distributor. There is all the particles are here, and the outlet is here from the top. The dead outlet. Sorry, I wasn't explicit. This should be. This does not mean the arrow. This means the primary gas actually goes here. Not it. It should not mean that it goes from the side and then goes through the distributor. It means it actually goes underneath the distributor to start with. You can make it in the lab, in the workshop. Easy. Super easy. Only thing quartz do not like is what? Huh? Yeah, nothing will like it. Yeah, absolutely right. Yes, steam. At high temperature and steam, quartz you will lose it after one run. It will crack. Huh? No, after one run. During the run, nothing will happen. And this sort of rigs, the most important thing is you need to heat them up and cool them down at a very controlled rate. Otherwise, the thermal cycling at a rapid rate, these ones do not like. So if you think I have a meeting with someone or have a restaurant party in the evening, I need to finish my experiments to go home early. There's accelerate it, cool it quickly, and start it. You will be up for trouble. This one's very quick, very quick. As long as you, what's steady state here? Temperature, remember. As long as you have detected that you have reached a constant temperature and the temperature is sustained for 4 or 5 minutes, that's it. Go ahead with your cold fit. How long it takes to go to that? Yes, that's right. During all the time, almost all the times, particularly with my not so good students, I'm with them during the startup. Because if anything happens, then I am the poor fellow who has to bring the money. So during the startup, I am there. Okay. The reason I'm saying is that we don't go beyond 10 degrees or so per minute. So it takes 2 hours, 3 hours, depending on what temperature you want to achieve. In the larger rig, we go to 1600. But then what's slow and steady wins the race. Never accelerate. Always much better. Metal, I think it will be even more important because metals have even more thermal lag, I would say. But our other reactor is, because it's a higher temperature, so we are using aluminum. What complications would be there?
Can you say what we are using is what you are using?
What have you been for what
This sort of thing do come from experience. I mean, you will not get a supplier who can go and tell that, look, I want this to give me a drop-in furnace to give you,
which will feed 1 gram per minute and develop 1100 degrees centigrade. No one will be able to give you that. So you have to design it on your own. Comes from a bit of experience, but then nothing is complicated. Everything in life is simple. If you think it's complicated, it's complicated. PhD work is very simple. Only thing you have to work smart. Experimental work is no difference. What's complication? Nothing. Easy, fun.
can anyone give me an idea why Gaia? What does the Gaia do? One thing that moisture analyzer, the gas analyzers do not like, particularly gas chromatography, that you can have different colors. These are all capillary colors. In the gas chromatograph, the most expensive consumable part is actually capillary colors. So they don't dry one of it. So you need to bone dry the gas. So we have a dry ice unit. Just normal water ice will not do it. Dry ice is really important. Did I answer the question? If you have dry ice, it will condense out the carbon. Dry ice dry ice temperature? What is the amount of downtime?
This gas analyzer calibration has been done for these 5 gases. What if some unknown gases, like something which we don't expect? How do we tackle such a problem?
So, from experience and from classification, we know that
these are major gases that will be evolved, and these are my major gases that I really need to identify and measure accurately. So you have to have the gas chromatograph calibrated for those gases very, very definitely. Now, your question then is, how many gases you can do it? Say I haven't mentioned their CXHY, the hydrocarbons. Predominantly it is CH4, so C1. But then technically there are also C2, C3, C4 up to benzene and others that are present. If you want to measure for those as well, then you will be needing about 10, 12 different cylinders, calibration cylinders, next to your micro GC. We have a GC trolley, which carries its own cylinders, and these gases are very expensive, very expensive. A company will take about 3 months to make those gases, stabilize them, because of the way they prepare it is actually, they prepare it fast, then and then they over every day they measure the composition, and once they find that the composition has settled, then they will supply it to you. So that time is money to them. So these are very, very expensive. So one gas cylinder, at least in our case, is supplied by Air Liquide now, not BOC. It's about $1,500–$1,600. So you really need to be very, very careful. So the next question is, if there are any unknown ones, it's very, very unlikely that the unknown ones will be the major ones. But if you get a feel for what could be the pollutant ones, then there are other ways to do it. There are something called Kitagawa Cells, some of the kits, Kitagawa company, or Draeger, D-R-A-E-G-E-R, E with umlaut. They sell, these are all single use. Each tube costs about $12 or $13. You take the sample, draw it through it, and then over a graduated cylinder, through the color change, it tells you how much of that particular gas. So for every type of gas, you can go to Kitagawa's website and then find it. But it's a very expensive way of dealing with it. But the good thing is, you literally know what are your major species that you will be looking at. It is extremely unlikely. I have never come in my life a situation where there is an unknown gas of completely unknown gas with major concentrations. So dry ice is a quenching unit. Dry ice is a quenching unit, which will quench out tar as well, everything.
So this residence time is for the whole particle?
Particle residence time, which is important.
Gas residence time would be different. If we are recycling it, then fresh gas will be coming every time, in every cycle.
We are not recycling anything, fortunately, here. We cannot recycle anything in this sort of rigs, impossible. I will never attempt to engineer such a solution. But it's a good point you allude to. In a drop tube furnace, the particle residence time and the gas residence times will be different. The particle residence time can be calculated from Stokes' law and the conditions. Gas residence time is very simple. Volumetric flow rate divided by appropriate cross-sectional area. Entrained flow, you need to keep them the same so that the particle cannot go ahead of the gas. That's the point that I've been making since yesterday, that if it goes away from the gas, which it will try to, then you will be losing the particles carbon, which you don't want.
Maximum.
Distribution of particles, carbon diameter will take most of it. It will mathematically ensure that this will take this much. Because it will swell also and it will reduce the increase diameter or maybe reduce the diameter.
All sorts of computations can be done. Unfortunately, we don't have a swelling code. So that releases one problem in our case. But you might
Right? That's why, as I showed yesterday, that knowing the particle size distribution accurately is extremely important. And you cannot just get it from the sieve sizing, because sieves are fast cut impression. Sieves are notoriously prone to clogging, and sieves, and therefore you have to complement that with laser diffraction sizing, which I mentioned in day 1, and the principle at which it works. Sometimes you need to complement that with quick SEM, scanning electron microscopy, just the morphology. So these days it's all desktop SEM. You just chuck it there. Within 1 hour, you get many, many samples measured, the particle size distribution. You really need to do that. Shortcutting there means your results will be unpredictable. And you learn in the process. That's the fun part of it. Yeah. If your gas composition changes completely, then you have to look for particular type of changing the columns. So there are different columns that you can put. So for example, in some of my experiments where we work with the waste tire, pyrolysis of waste tires, there the gas composition is very different from the gas composition that we measured from biomass pyrolysis or biomass gasification. So we use different types of columns, because I don't want my column used for biomass or coal to be contaminated with those coming from the other types of feedstock. So it's a matter of changing the columns if you are changing the fuel, but if you're not changing, that's fine. Important thing is to keep it healthy all the time, and the manufacturers will tell you, if you push them, how to best maintain it. Most of the time they don't want to tell you, because they want it to fail so that they can sell you more. So you need to know your tricks. Any other question? Where? Oh, here. I have taken it from one paper. He collected it, he cooled it, and the next day he ran it. That's why. But in this, there is no automatic recirculation of it. Very good, very good, very good question. Sorry, I should not have picked up this particular figure. I lazily, as I was sitting over there at the back, I picked up whichever was available to me that I could download. But it is not an automatic hot sample at the bottom being recirculated. That will be too difficult for me to design that system. In this case, it's only 1,000 degrees. In the next one, yes. Any other question? No. So it is, as I said, it's a very simple thing. It's a run. Why are you smiling? Everything in life is simple. Nothing is complicated. So anyway, when you do the pyrolysis, this is some of the results that we got. The reason I'm trying to show to all of you is not to make you an expert in brown coal or biomass pyrolysis or gasification, but to just to give you a feel for what is involved, what you can measure, what you cannot measure, nothing else. So look at those numbers or the figures from that point of view, and nothing else. So you can literally, measure the composition of the gases that you are interested, whatever, and these are the ones that we are interested, and we measure them because it's a very highly isothermal rig. Highly isothermal rig. I mean, the temperature is maintained because electrically heated, we have calibrated it, and it absolutely no temperature variation whatsoever. So, so scientific information wise, this is the sort of information that you can get. How much, and of course from there you can calculate what the total gas yield is. So one of our objective is fulfilled in that manner. If you,
So which one is increasing? So which one is decreasing and which one is increasing? And remember, it is pyrolysis.
so remember the first day that we said is the volatile matter, which is the main thing that comes out during pyrolysis. And as you increase the temperature, you get more volatiles out, and that's why the need for fixing a standard at 900 degrees centigrade 7 minutes came in. Otherwise, you will be nowhere. The important thing that we're trying to re-establish here is that as you increase the temperature, your total gas yield is actually increasing. But for this type of coals, what is the partitioning between the different types of the different components of the gas in the volatiles only, that is shown by this one. And this is a important information for us to have. Why? Because when we do the gasification, then we should be able to subtract this, gasification of the coal, then we should be able to subtract it from that and then say that, okay, this much contribution has come from the char gasification and this much has originated from the pyrolysis only. So that's where the importance of this information is. So CO concentration is one important aspect, and the second graph on the right hand side, which shows there, and these ones, by the way, were done under drop tube conditions, not under entrained flow conditions. So I wouldn't say that this will be a reliable predictor for entrained flow conditions results at all. But there is a whole lot of difference between the red and the black ones. As you can see, how much a difference it is. Purely by measurements, these are the black ones are the values at about 6 seconds per gasification. I forgot what's the particle size range used in this case. The paper should say that. But then when they try to make the estimates based on TGA pyrolysis data for a prolonged period, they were estimating a lot more. But we are not getting that one at all. Our actual measurement under the drop tube condition was a lot less, which is not unreasonable, because in the drop tube what's happening is the particles are not staying with in the environment. They are just going away. And the environment there is the pyrolysis environment created by high purity nitrogen. So this essentially shows that the drop tube measurements are subject to fallacy. It will give you false information. But it's important to bring it out in the open, and that's what we did. And then the students also looked at the CO2 gasification, what's the input CO2 concentrations, the effect of that one. If you, for a given feed rate of coal of a certain size, and here they looked at two different types of brown coal. The Ialon one is a very high iron containing brown coal. The Morwell one is the high calcium containing brown coal. That's the major difference. Carbon content wise, ash content, dry basis wise, they're similar, very similar. But the ash was very different. Ash composition is very different. So we looked at, okay, what's the main product from CO2 gasification, which is CO, how its concentration changes if you put in CO2, varying levels of CO2 as gasification agent. And that's what this shows. And as you would expect, the Bordeaux reaction will be the dominant one, C plus CO2 giving you 2 carbon monoxide. So the CO, all the CO2 that's coming in, that's taking out the char from the pyrolysis, char carbon from the pyrolysis, and giving you high CO. So if your downstream process, whether it's chemical synthesis or anything else, requires a high CO level in the gas, CO2 gasification is the way to go. And CO2 is available plentiful. But if you have too much CO2, then what will happen? Tell me. When you have fixed your coal feed rate, which is here 0.6 gram per minute, so it's a very well controlled, 600 milligram per minute, and then you are increasing CO2 percentage. Yes and no. That's number one. Number two, carbon is. Yes. So you were saying that as soon as you fix the mass flow rate of coal, you have fixed how much carbon you are putting in. So for that, there is a maximum amount of CO2 that you believe you can. That's stoichiometry, right? So beyond that, whatever CO2 will fill, that's coming to nothing. It's meaningless. It's not doing it. Very good. Your answer is also correct. That's why I say yes and no. Yes, it can take away the hit, but given that we have designed it in such a way that we are maintaining the isothermal nature of the inside of the reactor while the reactor is hitting, we are not going to do it. So you are not entirely wrong. Okay. So that's what it is. Again, the purpose here is to demonstrate what can be done, simple things. And then the other thing is, of course, the carbon conversion, or in this case, it's char carbon conversion. We are not talking about the volatile carbon conversion, because the student did produce char by two different means. One is in the TGA overnight at the same reaction temperature in the drop tube furnace at 1000 degrees. The TGA goes to about 1250 degrees, so that's not a problem. And then also they generated the char through pyrolysis inside the drop tube furnace one day, sufficient amount of char from the coal. And then the next day or another day, use the TGA char in one experiment and the drop tube char in another experiment. So what you are seeing in here is the carbon conversion in the char generated previously. So it is not the coal conversion that you are looking at. It's as if the volatile has been taken away, but you know, how much volatile you have taken away is subjective depending on that temperature. So that's why they did the pyrolysis at the same temperature to produce the char as the temperature of the CO2 gasification. Those have to be the same. Otherwise, if you are doing the char pyrolysis at 800, and then using that char to do the gasification at 1000, it will not be comparable, not be apples with apples. Okay. So this is what we said. So that is found that okay, in order to do that, you'll need a very long residence time. 24 seconds is a very, very long residence time if you are limited to 1000 degrees. So, and then he looked at, of course, he did many other experiments as well and quickly discarded them. That at what is at this temperature, what is the carbon conversion at that temperature, which is bugger all. At that temperature, not much, and then you can see a massive jump, and then finally at 1000 degrees or so, whatever happens. But the fact is, 1000 degrees for char, highest char conversion, 1000 degrees is not a good, is low. I mean, you can do it provided you can have a very tall reactor that can give you 24 seconds. But remember, if something is running at 10 meters per second, how long it has to be for 24 meters per 24 seconds. So then the other things that you can also determine from in here is that is if your gas composition is reaching equilibrium or not. So equilibrium gas composition calculation is very easy, right? You know the equilibrium constants. You find the Gibbs free energy, set it to 0, and then do a little bit of manipulation, and then you can calculate what will be the equilibrium gas composition. So that horizontal line at the top at that particular temperature. By the way, so you have the equilibrium constant. Equilibrium constant, and so equilibrium constant, does it depend on pressure? How many people are in favor saying
some pressure?
Depends upon the reactor, how much of the reactor. Order of reactor.
Equilibrium constant depends on temperature. If you look at the definition of equilibrium constant, the concentration of the products divided by. Very important to remember that. Again, the point I make is that we can do all these experiments, and feel great that I have designed a reactor and how good it looks and fantastic if you come and see and take photographs of the other video. But at the end of the day, what you use it for, how you analyze the data. That's where the fundamental chemistry knowledge, science knowledge is required. You cannot bypass it. So sometimes I ask this to take questions, not to denigrate you, but to really express. Anyway, so it's very important that we can make this sort of calculations also. Yes, I have designed it, but in my reactor, it's not reaching equilibrium composition unless I'm giving it a very long time. So my intention there will be to actually design a reactor where I can get highest possible gas composition, which is equilibrium gas composition, highest possible, close to within a time period residence time, which should be acceptable to the technology vendors. If I tell Mitsubishi, give me a gasifier 34 seconds, because I know it will give you, they will say, no, we don't do it. So that's the beauty of this sort of experiments and the analysis that's all simple things, simple things. So I always maintain that these things have become more and more simple when you start looking more deeper. And it's much more complicated. The other thing that you can do is you can also look at this sort of thing is the morphology change of the particles that we collect, whether that is ash or carbon filled particle char, which is carbon filled ash. Then how the surface actually looks like. Does it look like still carbonish, so that the gasification agents can still have the opportunity to enter into them and react and give you the gas that you want? Or is it becoming carbon? The minerals that come out from inside, rendering them inaccessible to the reactant. So this is what you can do by collecting the char and then looking at them under the electron microscope. So we actually looked at, the student looked at the char collected after different series of experiments. 12 seconds experiments, 24 seconds experiments, etc. Correct. So after pyrolysis, it looks quite good, very, very porous. This also is quite porous. The carbon has gone out, but the remaining surface is now getting coated with something else, looking very different. If you take the colored one, then it will become very clear. If you take the EDX, then it will become even clearer what it is. So SEM is a wonderful tool. I was talking to one of my students early this morning, 3:30 here, time in here. She was doing SEM on some of our catalyst samples. She was making them acidic, giving them acidic character. She's starting something called Sabatier reaction. How we can improve it? Let's know it's producing methane from carbon dioxide with hydrogen coming from biomass. So that's the whole purpose of it. So one thing to say that I have acidified it, but to what extent I have acidified it, you never know until such time you have done the analysis to both TGA and the SEM. The SEM actually, with the EDX, it actually tells very clearly that what has gone in and what has been displaced, all sorts of things. Anyway, let's not digress. So at the bottom. Oh no. Here. No, you can make it any seconds, up to 24 seconds, depending on the velocity of the gas that you use and the particle sizes. So some particles, if you use small particles, they will take longer to drop. If you use larger particles, it will take shorter time to drop. So that's how you can vary them. And because you need to know that accurately, you need to prepare your cold samples very accurately, and that's why we keep the feed rate so small, because preparing sufficient quantity for one run, and one run is about 3-4 hours steady state, so that you can fresh. Correct.
now again putting it in another run where it is all new ones, not mixed with the original code. No, no, you cannot do it. Cannot do it. Ooh, I was supposed to have brought something for him tomorrow maybe. Okay, so then we realized that it is, the small one is not giving us the right, okay, so this is the right time to break. Because if you don't tell me to stop, I usually don't stop.